Alright, we're going to start now. So we're going to continue from the nomenclature of alkane, but now it is cycloalkane. So we know for the linear chain alkane or branch alkane, non-cyclic alkane, so let's know that. So now we're going to go to cyclic alkane or cycloalkane, you're going to call that, right? So let's start from this simple one. So you don't have any substitution there. You have just the ring of carbon atoms, right? So all carbons are saturated. So you don't have double bond, triple bond, anything there. Just a single bonded carbon with a ring, right? So the simplest possible one is going to be this one, right? You have the 3 carbon atoms that are going to make a ring. You just have the hydrogen atoms there. There is no other substitution on that. So this is non-substituted, the simplest cycloalkane, which is of 3 carbon, right? So if it is not cyclic, like say for example like that, so you have hydrogen over here, so you're going to call propane for that, right? You have 3 carbons, it is propane, right? But now you have this cyclic one, you have a ring, then still you're going to call propane because you have 3 carbon atoms there, but you're going to put cyclo before propane, right? So this is cyclopropane, right? Why cyclo? You have the ring of the carbon atoms, right? That's the simplest one. So what you do? You're going to add cyclo, this word or prefix, you're going to call it. So prefix cyclo followed by the whatever carbon atom number you have. Propane, butane, pentane, hexane, alkane, whatever you have. Right? So that's how you're going to name it. So what about this one? So you're going to do the same thing. You're going to write cyclo because it is cyclic compound. And then you're going to count number of carbon atoms there. So you have 1, 2, 3, 4, 5. So pentane is for 5, right? So cyclopentane. That's how you're going to name it. So the other one, so the second one, it is ring compound. So you're going to write cyclo as a prefix. Then you're going to count number of carbons there. So how many? You have 7 in total, right? So heptane is the name for that. If you have 8, octane. If you have 9, nonane. 10, decane, like that. Right? You have that in the table, right? So that's how you're gonna name. So the simple one gonna be non-substituted one gonna be easy. Just write cyclo followed by the name for the carbon atoms. How many carbon atoms you have for that, right? So now, let's say we have substitution on that. So now, what I'm gonna do is I'm gonna take this hydrogen out from here, and then I'm gonna have non-hydrogen group like a methyl, ethyl, whatever you have. So you have the attachment over here. So that's gonna be the substituted cycloalkane, right? So as an example, so let's say this is methyl, right? So I'm gonna put over here. So now you have the cyclopropane, but now it is substituted cyclopropane because you have the methyl group in place of hydrogen. You have the one substitution for one hydrogen. Okay? So now this is this class, mono substituted, because you have only one substitution there. If you have on the other one, gonna be di substituted. If you have 3 hydrogen substituted with different groups, this is tri substituted, right? So here only one, so this is mono substituted. So if you have this case, how are you going to name that? So what you're going to do, is you're gonna write the whatever ring compound you have as a parent. And then whatever you have the substitution there, they're gonna be the branch, like other rules we went through, right? So you're gonna write the parent first. So as an example, for this molecule, cyclic part gonna be parent. So I'm gonna write cyclo, and then you're gonna count how many carbons over there. 1, 2, 3, 4, 5, 6. So you have the 6 carbon as a part of the closed loop ring, right? So then for 6 carbon, you're gonna call hexane, right? So cyclohexane, this is parent, like before. So if you don't have any substitution, you're gonna call that cyclohexane. So now you have substitution, right? So then you're gonna deal for the substitution later. So now this is the substitution you have. That part, like a branch, is gonna go before the parent, right? So you have 3 carbons. You have the bond in the middle carbon. Then what is that? It is propyl, but in the middle, iso, right? So you're gonna write isopropyl for that. Isopropyl, propyl. So this is the branch, right? So you're gonna write over here. Isopropyl, and then cyclohexane. Cyclohexane is the parent, and the branch on that, or the substituent on that, is isopropyl. So you're gonna put that before the parent. So isopropyl cyclohexane. That's how you're gonna name it. You're gonna follow the same rule for the next compound, right? So here you have different number of carbon, of course, right? So for this one, the one on the right. So what is the parent? Cyclic part is parent, right? So you're gonna count number of carbons there. So you have 1, 2, 3, 4, 5, 6, 7, 8. You have the 8 carbon. So what's gonna be the parent? This is gonna be cyclooctane. That's the parent you have. Okay? Then you're gonna deal with the substituent. So you have this part as substituent. Okay? So don't count the carbon that is part of the ring already. So don't count this for the branch. So other than the one you have in the ring, gonna be part of branch. Okay? So how many? You have 1 carbon over here. You have 1 carbon over here. You have 2 carbons. So you have 2 carbon. So what's gonna be the group for that? Ethyl, right? So we're gonna write ethyl cyclooctane. That's how we're gonna name it. Right? You're gonna follow the same rule for all monosubstituted alkane, cycloalkane. Right? So now here you may be wondering, what about the carbon labeling? For the one substitution, you don't need to label any carbon atom, because we're going to start from the numbering from the branched carbon. So if you want to number this, so this is going to be always carbon number 1, this carbon. For the second one, the same thing. Whatever carbon you have the substitution, that carbon is going to be always number 1. So this is obvious. You have only 1 substitution there, that carbon is going to be number 1, obviously. So you don't need to indicate any numbering if you have the mono substituted. Okay? But if you have di or tri, of course, you're going to indicate the labeling in which carbon you have the branch in it. Okay? Let's see the second one. There you have the 2 substitution there. It is di substituted. Now you have to number that. You have to label it. Okay? So let's see the first one. So again, the same rule. Whatever you have the part of the cycle, that's going to be parent, right? So this is parent. Always. So you're going to write cyclo, and then what's going to be the alkane after that? You're going to count number of carbons, right? How many? 1, 2, 3, 4. So cyclobutane. That's the parent like before. Right? Now you're gonna deal with the branch on that. So how many branches you have over here? So this is one branch you have, and this is another branch you have. Okay? So one is methyl, and then other gonna be ethyl. So you have two branches, right? So now the question is, in which carbon you have the methyl attached to? In which carbon you have the ethyl attached to? So now you have to number the carbon. Okay? So now the question is, you're going to start from the substituted carbon for sure. So you have two options. One, you're going to give the number 1 for this carbon in which the ethyl is attached there, or you can do the other one. So the one in which you have the methyl attached to, right? So you can have that, right? So two options. So which carbon you're going to choose? The same old rule. Ethyl, gonna take the priority, right? So that's why the red one, number 1 is correct, and then you're gonna have the number 2, and then number 3, number 4. So you're gonna go to counterclockwise. Now you may be thinking, why we don't go to clockwise? So why not number 2 for that carbon? Why not number 2? Not number 2. The same old rule. Remember, when you number that, you must have the branching as lowest labeling as possible when you number that. Okay? So if you go to the other route, you can have number 4 for the carbon that has methyl group attached to that. You don't go that long route. You're going to have the as lowest number possible for the next branched carbon. That's why we're going to go to counter. So you're going to have number 2 for the carbon that is attached to methyl. That's the reason why. Okay? So then what are you going to write? 1 ethyl, and then you're going to have 2 methyl, and then you're going to have the cyclobutane. Right? That's how you're going to name it. Okay, so if you have only one substitution, you don't need to bothering about the labeling. When you have 2 or more substitutions, then you have to label the carbon. So you're going to indicate which branch is on which carbon. Okay? So another example. So now it is obvious, right? So you have 5 carbons as a parent. So you're going to write cyclopentane, right? So cyclopentane, that's the parent you have. And then you're going to deal with the substitution. So you have the isopropyl, 1 substitution. Other going to be, you have 4 carbon there, 1, 2, 3, 4. So of course butane. And then with butane, you have all in 1 carbon branch. So tertiary or 3 degree, you can write that. So tertiary butyl. So then 1 tertiary butyl, you're going to start from here, because alphabetically B gonna come before isopropyl, right? So one tertiary butyl, and then you're gonna have 3 isopropyl and cyclopentane, right? That's how you're gonna name it. So now a little bit complicated. Let's say you have more than 2, 3. You follow the same rule, right? So first, identify the parent, okay? So here you have this parent, just a ring, right? So 6 carbon, so you're gonna write cyclohexane. So this is parent, okay? So now you're gonna deal with the branches. So how many branches you have? 3. So one gonna be methyl, other gonna be also methyl. You have 2 methyl there. So you're gonna write dimethyl, right? And then the other one gonna be ethyl. So you're gonna write ethyl, right? So now the next thing is numbering the carbon. Where are you gonna start numbering that? Okay? So if you have just 2, you're gonna have the number starting from ethyl compared to methyl. But you have 3. So if you have 3, the branching order, so in which you have the least possible labeling for the carbon that has the branch, they're gonna take the priority. Okay? So then where are you gonna start? So 1, 2, 3, 4, or you're gonna have 1, 2, 3, 4 like that. So of course the right way, right? If you do that, you're gonna have the most probable, because you're gonna have the second branching if you go to the red way. If you go to the blue way, you're gonna get the third branching there. So the second branching gonna be preferred rather than the third branching. Okay? So then you're gonna have the 1-ethyl there. You're gonna have the dimethyl in carbon number 2 and 4. So 2,4-dimethyl is after that. And then you have the parent cyclohexane. Right? That's how you're gonna do. And then the other example, you have the 3 carbon cycle. So what's gonna be the parent? So cyclopropane. So that's the parent. And then you have the branch, 2 isopropyl, 1 methyl, right? So you can write that, right? It's not different. Good. Any question on that? All right. So now, the next thing gonna be, so now we're gonna go to the different cyclic compound, and then what's gonna be the stability when you have different substitution on that. So whenever we deal substitution, we're gonna have 2 types of isomers in those compounds, right? Say you have the hexane, cyclohexane like that. So you have the 6 carbon atom in the ring, right? So right now it is not substituted. If you don't have substitution, you don't have any isomer, all gonna be like same, right? But if you have the substitution over here, then we're gonna call cis and trans isomers. Okay? So let's say you have substitution there, the methyl group. So I'm gonna put 1 methyl over here in place of hydrogen, right? So this is 1. So I'm gonna put 1 methyl over here. So now you have all non-substituted carbon, 5, but this is substituted. You have 1 substitution there, okay? And to the next carbon, let's say I have over here. So I'm gonna put another group into that. So I have, let's see, how are you gonna look? So this, right? So yeah, I have two substitutions. So whenever you have this condition, then you can have the cis or trans substitution. Okay. So how to distinguish that? So you're gonna see by the position of substituent. Okay. So suppose you have all carbons in one plane, right? And then what's gonna be the direction of the substituent? So this metal is towards you, right? What about the other one? Towards you, right? If you see the back side, you don't have any substituent over here. Both substituents are in one side of the plane, like this, right? If you have that, this is called cis. The name, this, gonna be on the same side. If you have the substituents like this one, right? Both metal are on the same side of plane. You don't have any other metal to the other side, right? It is called the cis. So how to draw that? If you have this condition like that, both are towards the viewer. Okay? If you have that, the example drawn over here is good. So this is towards the viewer. Okay? So this is what drawn over there. Both methyl are towards you. You are the viewers. Okay? Now what if both methyls are away from the viewer? So now both are to the other side than the viewer. How are you going to draw it? If you have that, you're going to draw like this. So you're going to have the 6 carbon atoms there. Okay? And then I'm going to write like that. And then I'm going to write like that. So this is also cis. So this is going to be away from the viewer. Viewer, right? So both are cis. Don't be confused with that. So if you have both towards you, you're going to have the bold line over there. Like this case, this is cis. Okay? If you have like this, also both are on the same side, but going to be away from the viewer, you can have the dotted line for that. As long as you have both bold or both dotted, both are cis conformations. Okay? Now what if I'm going to change the position of that substituent, and then now I'm going to put on the other side, like this, right? So now these 6 carbons are in one plane. So now if you view from your side, one methyl is towards you, toward the other one. Other one is away from the plane, right? Opposite side. If you have this, then it is called trans. Okay? So this is trans, in which you have one away from the viewer, and the other one you have towards the viewer, opposite side. So one bold line, other dotted line, that means they are in the opposite side. The substituents are in the opposite side. This is called trans. Okay? So that's how you're going to distinguish cis and trans. So based on the plane of carbon, in which side you have the substituent is. Right? So now this is clear. Okay. So now we're going to see about the stability. So you have the different cyclic alkanes. So which gonna be more stable, which gonna be less stable, right? So we're gonna compare those things over here. So let's see the simplest one. So that's gonna be the propane, right? So I'm gonna show you how it is less stable compared to other higher member cyclic alkane. Okay? So I'm gonna show you two structure. So we're gonna compare that. So it's gonna make sense. When you say stable or less stable, like that. Okay. So let's start from the methane. Okay. So this is stable molecule, this is saturated. So suppose this is methane, right? So you have the carbon, central carbon, you have 4 hydrogens there. So what's gonna be the angle between these two CS bonds? I mean that angle. So the angle between these two CS bonds, this angle. So what's gonna be that?
109.
109.5.
109, right? So 109 is gonna be that, okay? So this is the angle in which they are relaxed. You don't have any strain over here, right? It's not cyclic, no strain. So the relaxed condition, you have the CH angle 109. So now you're gonna force 3 carbon atoms to make the bond, right? So what's gonna be the angle between 3 carbon atoms, like that angle? So CC bond and another CC bond, so that angle. So what's gonna be that? 60, right? So this is gonna be about 60, so it's shown over here, right? So now, so other two, they are relaxed. You have 109 around for that CH, right? But now your one angle is forced to be 60 rather than to be 109. So then what do you think? This is gonna be more stable than the relaxed one, or this is gonna be less stable? Of course less, right? So that's the reason why when you deal those thingy, we're gonna say 2 things for the cyclic compound. One gonna be, of course, angular, that results from the angle. So if it is different than 109, you're gonna have the angular strain there. That's gonna make less stable. Okay? So you are forcing that to go away from 109. So less than that, right? So the second thing gonna be the torsional strain. So what that means is, whenever you see the first CH to the second CH, okay? So here you're gonna see those far, but in actual molecule, you have the van der Waals radii just crossing together. So if you have both in the same direction, then you're gonna have the crowding between these 2 atoms. They're gonna make less stable, right? If 2 hydrogens are like in the same plane, both in same direction, they're gonna make the torsional strain. So the torsional is whether they are on the same plane or they are away like that. Remember, if you have like this, it's gonna be eclipse type of conformation, right? If you have away about 60 degree, then it's gonna be like stagger, right? So if you have like this, it's gonna be more stable. If you have like this, eclipse, it's gonna be less stable. So 2 things. One, whether you have the neighboring hydrogens eclipse together or not. So that is one point. Other, what's gonna be the angle when you make the ring? 2 things. Okay? Obviously, this is cyclopropane, so it's gonna be less stable, right? Let's see the little bit larger ring. So that's gonna be 1 more carbon, cyclobutane, right? So now, what's gonna be the angle for cyclobutane. So you have one more carbon, a little bit more than that, of course, more than cyclopropane, right? So angle gonna be 90. So still it is less than 109. So you have the angular strain there, so still for the cyclobutane, right? What about the torsional? So they are equilibrium in the same direction. So you have some strain, but of course lower than the cyclopropane. Okay, so both the strain, angular and the torsion strain. So these two are less in cyclobutane compared to cyclopropane. Okay. So now let's see one more carbon, cyclopentane. Now you have the 5 carbon atoms there. Okay. So of course, gonna be more than cyclobutane, right? More than 90 degrees. So what's gonna be the angle? If you measure, that's gonna be 108. So close to 109, right? So you have very less strain, angular strain, if you compare with cyclopropane or cyclobutane. Okay, you have very little. So what about the angular torsional? So you're gonna have torsional strain also low, because now they are not exactly eclipsed, so they are just a little bit going away from the plane. So you're gonna have that angle. See, it's not 0. It's not exactly 60. If you have somewhere over here, it's gonna be 60. So you have less than 60, but it's not eclipse towards the stagger. Okay. So overall, if you compare cyclopentane, it has a less angular strain than cyclobutane. It has a less torsional strain than cyclobutane. Okay? Let's go one more. Cyclohexane, right? So this is this one. So we're gonna focus mainly on this one. We're gonna see a lot of confirmations on that, right? So you can expect question in your exam too, also in ACS exams. Okay, this is very frequently asked question. So now you have the cyclohexane, right? So now let's see the angular strain. Do we have any angular strain there or no? Right? So it is perfectly 109, like methane. That means you don't have any strain as a result of that angle. You have the carbon-carbon-carbon angle, this one. This is same as carbon-carbon-hydrogen. This is same as hydrogen-carbon, hydrogen-carbon, hydrogen, right? So all angles are about 109. So you don't have any strain as a result of the angle, like lower member cycle. Okay? So no torsional. Also because you're gonna have, if you see this way, you may think you have on the same plane, right? But it's gonna be like a twisted one, like this one, right? So it's gonna stay like this. So it's not exactly in one plane, all the carbons, it'll be twisted. We're gonna see the confirmations later, all detail. So the hydrogens are not eclipsed. Okay? So you don't have any torsional strain there. So now, confirmations. So how many different ways the carbon atoms and hydrogen atoms gonna take in space when they form the molecule, right? This is confirmation. Okay. So one way, the one that is most stable, gonna be like this. So let's say this is one plane, right? So you're gonna take the carbon atoms like this. So normally the 4 carbon atoms are gonna be like close to planar in one plane. and then one carbon gonna be away from the plane, right? So if I show something like this, so the central four carbons gonna be like in one plane, and then this gonna be away towards you, the other carbon, this carbon, okay? So this gonna be out of plane towards you, and then the other one, so this one gonna be on the back, this carbon, right? So out of 6 carbon atoms, those 4 gonna be nearby the plane, and then the one carbon gonna be below the plane, okay? And the other carbon gonna be above the plane. So that's how the stable form gonna look like, okay? So if you have that's gonna be called the chair conformation. It's like a chair, right? So one is down, so this gonna be below the plane, and then other 4 gonna be like you have the place to sit over there, and then the top carbon gonna be like back for the support, right? So gonna be away from the plane, something like that, right? So the 4 carbon, and then one gonna be out of plane, the lower carbon, and then the top carbon gonna be also out of plane. One in one side, other gonna be in the other side. If you have that, this is called chair conformation. That's the name for that. It's like a chair. Okay. So now when you label that, so you're gonna label something like this. Of course, based on the substituent you have there, right? So you're gonna see which carbon atoms are in a plane. So I can label like carbon number 1, for example. So 2, 3, 4. So those 4 gonna be close to planar. So this is planar, right? In the same plane. And then 1 gonna be above. So this gonna be above the plane. Above the plane. And then the other carbon gonna be below the plane. Below the plane. Something like that. Right? So if I label 1 through 6 like that, so what I can do is I'm gonna take those 4, so number 2, 3, 5, 6 gonna be in one plane, right? Like that. And then number 1 gonna be above the plane. This is towards you. Number 1, this carbon. And then you have the number 4 gonna be behind the plane. It's gonna be twisted towards me, like that. Okay. That's the chair conformation. So the next one gonna be the boat conformation. So now what if you have the chair conformation, right? So you have the 4 carbon atoms in one plane. Let me write this way. And then for the chair, you have 1 carbon towards you. This way. So you have 1 carbon towards you and the other carbon gonna be towards me, right? What if I flip that to make towards you? So now both carbons are towards you, N carbons, and the 4 are on the plane like before. This is like a boat, right? So this is called boat conformation. Right? So remember, so you have 4 carbon atoms. So these 4 are on the same plane. Let me go from here. Gonna be here. This here. So these 4 are gonna be in plane, and then 1 and 4 are on the same side of the plane. If you have that, it's gonna be like a boat, right? So twisted boat gonna be, you have the boat, but you have a little bit twist on the 4 carbon on the plane. If you have twist on that, it is called the twist boat. The name, right? Now let's see all together. Now you see the energy profile. Which is gonna be more stable, which is gonna be less stable, right? So, which is gonna be the chair conformation, So it is written over here, right? So this is here, this is here. So you have the minimum energy for those two, right? So the less energy, okay? So less energy, or the least if you compare all different confirmations, okay? And then what about the boat? So without any twist, if you have all four in one plane without any twist there, so you have four, that is 2, 3, 5, 6. So for this, 2, 3, 5, 6 are in a plane. In a plane. Okay? So, if you have that, you don't have any twist there. You don't have any twist on the central four carbons. Okay? It is the simple boat conformation. So they're going to have the energy like this. Right? So if you see the energy, going to be like that. That energy. Of course, higher than the chair. Right? What if you have the twist on the plane? So now you have the 2, 3, 5, 6 are not in a plane. You have slight twist on the plane. So here 2, 3, 5, 6 are not in a plane, right? So you have slightly twist out of these four carbons. Of course, still the end carbon is going to be in one side of the plane, up or down, both in one side to make boat, right? So these are the twist boat. So which conformation going to have the least in energy? Of course, chair. Which going to have the most in energy? If you have only one chair and half of the chair, so only one twist, all are the same plane. So this is going to be the highest energy. Board going to have a little bit less than that, and then twist going to have a little bit less than that, right? So probably one thing you are confused about is twist, the term twist, right? So this term gonna say for the central four carbon. Don't be confused with the end carbons, okay? To be both, always end carbon gonna be in one side like that, okay? So it is talking about the central four carbons. So not the end carbon that is above the plane. So I can do it. So if you see that, so the paper gonna have, let me put my hand, gonna be easier. So my hand is touching four carbon atoms, right? So this carbon atom, this one, and then this one, and then this one. These are the four central in a plane, right? So it is not, the twist is not saying for this carbon. This is above the plane of four carbons. It is not talking about this one. This is also above the plane of four carbon atoms, right? So these two are gonna make a boat, right? So the twist boat is talking about the central four carbon atoms that are in a plane, right? So now, if I do twist like that a little bit, it is boat, but four carbon atoms in a plane are not perfectly in a plane right now. So they're gonna be a little bit twisted from their position. That is twist, right? That's what it means. All right. So you have all the energy values over here, kilocalorie, kilojoule, right? You have different units there. So these are the confirmations. Chair, half chair is only one flipped, and then boat, when you have both flipped, and then twisting boat, when you have a little bit tilted plane of four atoms at the middle. Right, so these are the confirmations. Any question on that? Let me know if you have any confusion. All good? Now, if you have question in the exam, you can answer that, right?
Yes.
So you know which confirmation is going to be more stable? Chair. Which is going to be least stable? Half chair, right? And then which is going to be more stable? Simple boat or the twist boat? Twist boat is going to be more stable, right? That's the question I'm making. So we have 2 minutes. So now let's define the position of hydrogen. Okay? So now it is a little bit difficult to visualize. So if you see the ring like that, so you have 2 different types of hydrogens over here. Okay? In terms of the position. So you have the one type of hydrogen, not only one base, one on each carbon. So total 6 hydrogens, right? So 6 hydrogens are like they are going perpendicular to the plane of the carbon, roughly. Okay? So one is like that. One is like they are going away from the flame of the carbon atoms. Okay? Based on that, this hydrogen type is classified by one name, and the hydrogen like this is called different name. Okay? So the one like this is called axial. So here, like those blue mark like that. So these type of hydrogens, right? So you have 6 in total. So 1 hydrogen in each carbon. So this is called the axial hydrogens, like that. So the hydrogen that is perpendicular to the plane of the carbon you have, right? So this type of hydrogen, this type of hydrogen, and then you're going to have this type of hydrogen. So that are perpendicular, nearly perpendicular to the plane. Okay? And the other type like this. So this is not perpendicular to the plane, it is going away from the plane. Right? So away from the other hydrogen, going to the other way. So this is called the equatorial. That's the name for that. Right? So this is going to point away from the ring, like this. Going to go away. You're going to call this equatorial. So remember 2 different types of hydrogens. Right? So how many total equatorial hydrogens you have for the cyclohexane? So 1 in each carbon. You have 6 carbon, so you're going to have these 6 equatorial. Okay? So how many axial hydrogens you have for the cyclohexane? 6, right? So you have 1 is in carbon, each carbon. So you have the 6 axial and 6 equatorial. So total 12 hydrogens. Okay? So we have a few slides. We're going to have our next class, and then we're going to start a new chapter. Okay? Thank you.